thank you all for coming. I think we've got a marvelous meeting for you here the next few days. We started off well this morning. We're going to have a very exciting afternoon, I'm sure. So we're looking forward to a record-breaking meeting, especially in terms of people's enjoyment of the meeting. So that's the key thing after all. As per usual, in the afternoon of the first day of the meeting, we have the Masursky lecture, and we also have some awards that are given to people associated with the meeting. And so we're going to start off right away with the presentation of the Dwornik Awards, and Danielle Wyrick is going to come up and take care of that.
Hello, everyone. For those of you who don't know, the Geological Society, specifically the Planetary Geology Division, operates a number of awards, including the Dwornik Student Awards here at LPSC every year. Just FYI, this is our current board. I'm the current chair, and James Ray will be handing out these awards and doing the photo ops today. He'll be our incoming chair next year. We are currently soliciting for our incoming Secretary of Treasury, so those of you that would be interested, please contact any one of us. We'd love to talk to you. Also for students, in addition to our standing board members, we have 2 student advisory members. Our senior one will be rotating off, and so we will be soliciting applications for our student advisory member June 1st as well. So please check out our website for those positions. That's our website, by the way. So one of our major awards is the Pellis Writer Award. This is given out for the best student-led author in a major publication. Last year's award was given out to Stephen Battaglia from Northern Illinois University for his paper on Io's theothermal, which sulfur, lithosphere cycle inferred from sulfur solubility modeling of Pele's magma supply. So I'm not sure if Stephen is here, but if we could give him a quick round of applause on that. The Pellis Writer Awards for this year, the 2 divisions, this is a joint award between Geological Society and the Meteoritical Society. We have met, the winners have been determined, but we're finalizing everything. So stay tuned, check our website, that'll be announced soon. The Shoemaker Award this year, this is an annual award. This is chaired by David Kring, and it's done for impact cratering studies. This year's recipient was James Keene from the University of Arizona, and James is going to be modeling the rational dynamics of the moon as it was affected by a series of impacts during the basin-forming epoch. So we'll look forward to seeing his results on that. The PGD's Distinguished Service Award this year went out to Mike Kelly at NASA headquarters for not only his service previously as a board member, but he has proved to be a long-standing volunteer at our booth and helps us in a lot of different ways. It was a well-deserved award. And so what we're really here for is to honor our students, which is our 2015 Dwornik Awards. So these were presentations at last year's LPSC, and we honor them this year with a plaque. For our graduate student category, our best oral presentation went to Robert Jacobson at the University of Tennessee. Is he here? Our honorable mention this year in the graduate student oral presentation was Elisa Santos. For graduate poster presentations, our best poster presentation went to Hannah Cicerni. Just for the record, she was, we had to have some interesting conflict of interest since she was serving on the board, but I assure you that she won fair and square and overwhelmingly in that category, so congratulations. Honorable mention in the graduate poster went to Jessica Watkins at UCLA. We also hand out undergraduate awards as well. So in undergraduate, the best oral presentation went to Jonathan Oulton at Florida State University. An honorable mention in the oral presentation category went to Roger Michaelides at Cornell University. And finally, our undergraduate poster presentation. So the best undergraduate poster presentation last year went to Hank Cole at Colorado School of Mines. And we also had an honorable mention of Amanda Stadterman from Washington University in St. Louis. And I really cannot emphasize enough, the number of applications that we get for the Dwornik Awards increases every year. I believe this year we have 139 students up for this award, and we cannot do it without judges. So for those of you that judge every year, thank you. You're what makes this possible. Those of you that have not volunteered to judge, we need you. And so please, if you haven't, it's not too late, please contact Brad Thompson. He'd be happy to take you as a volunteer. And that's it. Thank you.
We also have another group of participants in the meeting that we honor at the afternoon on Monday. And these are some very, very talented young people who applied for the Career Development Award that we provide out of the LPI. It's a very, very competitive competition, and we have the postdocs from the LPI help out with managing the process, reviewing the applicants. We get quite a few applicants, and coming up with a selection of the winning recipients. And this year's awardees, if you could just hold your applause till the end, and we'll get them all to stand up. Krissa Avdiadou, Thomas Barrett, Ernest Bell, Laura Corley, Matthew Cross, Karanam Prasad, Gavin Kelly, Levki Koop, Marie McBride, Kathleen Scanlon, Sarah Sutton, and Jason Williams. If you could all stand up and give them a round of applause. And please, you know, we're really, really excited to have such a great group of people participating, a great group of awardees this year, and we look forward to their presentations. Thank you. And I will pass the baton to Eileen Stansbury, who will introduce the Masursky speaker.
Welcome, everyone. I'm glad to see so many faces here on Monday afternoon for our plenary. I have the privilege of being able to introduce our Masursky lecturer. Probably actually doesn't need much of an introduction, but Alan Stern is Associate Vice President of R&D at Southwest Research Institute in Boulder. He is previously an Associate Administrator for NASA's Science Mission Directorate. For this meeting is probably most well known this afternoon as the principal investigator of the New Horizons mission, but he has in fact done an extraordinary number of suborbital, orbital, deep space missions and instruments in his portfolio. And so without further ado, please join me in welcoming Alan Stern.
Thank you, Eileen. Okay. So the lavalier should be on now. Great. There's a lot of you here. I have to say, I think I stayed up too late last night to be giving this talk, but here we are. I want to thank Eileen for that introduction, and also I want to thank Steve and the program committee for inviting New Horizons to give the Masursky lecture. It's an honor for all of us on the team. And you know, it's a big team. People know the co-investigators, this big engineering team, big operations team, APL, Southwest, people from universities and institutions, including the LPI, all around the country. But I want to recognize one person who, unfortunately, I'm going to recognize them anyway, but it's that empty chair there. He had to get up and take a phone call about 2 minutes before this began. New Horizons would not have been possible without the support of Jim Green for the last 10 years across the entirety of the solar system. Okay, so I'm going to give a little bit of a different talk than you might normally hear. I'm going to be followed by 5 of my colleagues from the New Horizons team giving in-depth presentations on the geology and geophysics of the Pluto-Charon system, on the composition findings that we've got, the atmosphere and plasma, on the satellites, and on the origin. But I'm going to cover things a little bit more broadly because that's what Steve asked me to do, and to talk about a couple of topics that might not normally come up when speaking to an audience like this. But this is the first mission in the New Frontiers program, and I thought that his ideas were just spectacular, and so that's what I'm going to do. Unfortunately, I have too many slides for the amount of time that's allotted, so I'm going to buzz through it. So let's start with last year. This is Pluto. We've come a long way. Yeah, we've turned that point of light that Hubble could barely distinguish as a disk into a real system of worlds. And I think it shows the power of exploration. I'll say a little bit more about that later. But let me start, particularly for the younger people in the audience, and say a little bit about the history of the exploration of Pluto. At the end of the Voyager program in the late 1980s, a group of young scientists got together and dubbed themselves the Pluto Underground. They did, patterned after the Mars Underground, and went to Jeff Briggs, who was then the Planetary Division Director, and asked if NASA would study how to do a mission to Pluto. And that set us on a 14-year journey just to get permission to do it and to see NASA conduct a competition that ultimately the New Horizons team won. Listed here are the Pluto missions that didn't make it off the drawing board, and any one of them would have been spectacular. But I can tell you, having our team now carried out New Horizons, that there are a lot of lessons learned for all of us in those missions that didn't make it off the drawing board. And I know that many of you, like myself, right now are involved in Discovery or New Frontiers proposals. So most of those missions didn't make it off the drawing board because their science teams didn't have the appetite control to say no, and they got out of control on cost. And then the agency couldn't afford it or didn't want to afford it, and one after the other never made it to the launch pad. So if you're thinking or writing proposals right now, my very best advice from the lesson we learned on New Horizons is it's better to have 80% of something than to have 100% of nothing. It's true. So how did we actually get to do this? So, we knew from ground-based studies and Earth orbital satellites that the Pluto system was super interesting. We knew, for example, that there were 3 active volatiles on the surface. You see at the top of this chart a mid-infrared, near-infrared spectrum, reflectance spectrum of Pluto showing the methane that was discovered first, then the nitrogen and the carbon monoxide. And this told us that it was going to be a really interesting and dynamic place because all 3 of these have different vapor pressures and transport around the surface differently. We knew that Pluto's density indicated that it was about 70% rock. And that was a little bit surprising to people that thought about icy planets, but you can't judge a book by its cover. We knew that the Pluto-Charon system, because of its specific angular momentum and other attributes, appeared to be created in very much the same way through a giant impact as the Earth-Moon system. And we knew that Pluto had an atmosphere, even that the atmosphere had interesting vertical structure. We knew all of this in the late 80s and the early 1990s. And for that reason, advisory committee after advisory committee recommended that we study this further, or we try to get a mission started, or we put it at the top of the queue, and so forth. But it never really made it through to the top of a decadal survey process until the discovery of the Kuiper belt. And this is what really made the difference, because not just the existence of the Kuiper belt, or the fact that it's the largest structure in the planetary system, but the fact that we discovered that Pluto was not a misfit in the solar system, but the harbinger of a whole class of small planets that we didn't know existed until the 90s and the early 2000s. And as a result of that discovery, the 2003 Planetary Decadal Survey recommended this mission at the very top of the medium mission queue that became the New Frontiers program. And I'm very fortunate for that, and also very fortunate that our team was successful in proposing. And we had very tough competitors. And I'm sure that any of those missions would have produced spectacular results as well. But I'm going to tell you about New Horizons. So let me first say that we had a science definition team that John Lenine ran that put together 16 different objectives for this first reconnaissance of the Pluto system. They're listed here. Now, actually, for the announcement of opportunity, they were described in gory detail. So what kind of imaging resolution? What kind of dynamic range should you have? What kind of spectral resolution? What kind of sensitivity to the atmosphere? But let me just summarize the 3 primary objectives of this mission, which is very different from most of the missions that we fly today, because it's a mission of exploration and not a mission going back asking deeper questions. We're very simple. Map the surface of Pluto and its big satellite Charon, map the surface composition of the pair, and assay the atmosphere, its vertical structure and its composition, and determine its escape rate. And then below that, you see a set of secondary objectives that added depth in terms of trace species or higher resolution, or adding stereo so we could get the topography on the surface, thermal measurements, et cetera. And then there were a group of sort of nice to have, group 3 objectives. New Horizons proposed to do every one of these except for one, and that was to bring a magnetometer to search for a magnetic field. And that was primarily a cost issue, because although magnetometers are not expensive, cleaning your spacecraft magnetically and putting booms on it can be very expensive. So we proposed to do 15 of those 16 things, and in fact, by the time we got to the launch pad, our payload and our spacecraft were able to do all 15 that we had said in the proposal we would do. This is the payload that we flew. We built a very small spacecraft, and we made many compromises to save money. For example, we have a telecommunication system that, from a similar range to Voyager at Neptune, has a 10 times lower data transmission rate, because we wanted to make sure that we actually got to the launch pad. So we made compromises like that. We took a risk and proposed to do extensive hibernation on the way across the solar system so that we could have a much smaller operations team and save money as well. Where we put our money was in the capability of the spacecraft and the instruments to do a really spectacular flyby. So we made sure that we had very large solid-state memories on board so we could take a lot of data, and very fast bus speeds so that we could be taking data from multiple instruments at the same time. And we made sure of many other things like turn rates and power margins and things like that that allowed us to really operate the spacecraft at the peak of its capability. And then we put 7 scientific instruments aboard, and I'll tell you very briefly what they are. I'll start with the 2 on your left, and that's SWAP and PEPSI. They are plasma instruments, and SWAP was designed specifically to determine the escape rate from Pluto's atmosphere, and PEPSI to measure the composition of ions flowing off Pluto's atmosphere. REX is our radio science experiment. It has multiple objectives. The primary one is to do a radio occultation with a multi-kilowatt beam from the Deep Space Network, so that you can measure the change in refractive index as a function of altitude and recover the temperature and pressure structure of Pluto's atmosphere. But REX is also used to make brightness temperature measurements at 4 centimeters, and it's also been used in a radar experiment in which we just shattered all of the radar distance records by a factor of 300% and recovered the first radar reflectivity of Pluto. In addition, we flew an ultraviolet imaging spectrometer. It's called ALICE, and its job is to determine the composition of Pluto's atmosphere as a function of altitude, and with it, the temperature structure in the upper atmosphere. Ralph and Lori comprise our primary camera systems. Lori is a long focal length equivalent to sort of the Voyager narrow angle camera, but instead of a Vidicon, it uses a CCD. It's just a panchromatic camera. There are no color filters whatsoever. But because it's long focal length, it allowed us to do high resolution imaging of the surface, and I hope to show you some of that. Ralph is a much more competent instrument with many more bells and whistles. It's our color camera with 4 color filters. It's also a panchromatic camera, and in addition, it also carries an infrared mapping spectrometer that puts 64,000 pixels on the target and develops a spectrum from 1.25 to 2.5 microns at every pixel location, so that we could do massive amounts of composition mapping in a very fast flyby. And then we flew a dust counter, which is a student-built experiment done at the University of Colorado. And you may not know this, but New Horizons was the first mission to carry a student-built instrument on a planetary mission. And when we actually proposed to do that, it was very controversial. But I'm happy to see that today NASA requests that and that we see those kinds of instruments on Juno. We saw them on Grail. We see them on Maven. We see them on OSIRIS-REx. I think it's just great. And I have to tell you, of all the instruments that we put on New Horizons, not only was the student-built instrument the least expensive, it was the first one delivered. So they did a great job. Now, we had some challenges. As I mentioned, cost was a major challenge to New Horizons, in part because all the Pluto missions before us had tripped up over cost. And we were asked to do this on 1/5 of the cost of Voyager. Development schedule was another. From the day that we got a phone call that we had won the competition to launch was 4 years and 2 months. And that's a very fast development schedule for a deep space planetary mission. Compare it to Galileo, 12 years. Compare it to Cassini at over a decade. And it was really a horse race. And that was compounded by the fact that our launch vehicle didn't exist at the time that we were selected. The Atlas V was in development and not yet flown one time. And to get that qualified and get it off to a number of successful launches was a big challenge. But Lockheed Martin stood up to that challenge. Boeing as well, because Boeing provided our third stage. Instrument miniaturization. That was a big challenge, but NASA, fortunately, had spent money all through the 1990s for laboratory and breadboard development of miniaturized instruments for Pluto. And then we had to get nuclear launch approval, which involved 42 state and federal agencies, all having to say yes, ranging from the Coast Guard to the governor of Florida, to the Department of Defense, to the Department of Energy. You can go on down that long list. And typically, missions had spent 8 to 12 years getting nuclear launch approval. Doing it in 4 years was something we weren't sure we could do. It turns out that we were able to do that, and hopefully we pioneered a better way to do it for future missions. And we got to the launch pad, and we launched on the 19th of January, 2006, after that 4-year breakneck pace for all of us, and then flew to Jupiter 13 months later for a gravity assist and a science flyby, and did that flyby in early 2007, and then off across the entirety of the middle solar system to intercept Pluto in July of 2015 as it crossed the invariable plane, so the energetics were most favorable. So that was a long route of flight for us, but because we had a very small flight team, I'm told Voyager was about 450 people as it was cruising among the giant planets. We were about 50 people, and every one of them, including the PI and the project manager, were part-time. It was a lot of work. And when you see people in the hallways at this meeting who are on New Horizons, if they're wearing a New Horizons shirt or you just know they're on New Horizons, you'd do me a big favor if you said thank you, because they worked for 9 years straight to pull this off. We never had a break. We not only planned the nominal Pluto encounter, but 3 backup encounters. We wrote software for 150 different faults and put it on the spacecraft so it could take care of itself had something gone awry, and many other things. The actual encounter began in January of last year, and it's a 2-year-long event. It's still taking place for us. The first 6 months as we were on approach to the Pluto system, we were primarily doing environmental monitoring of the plasma and dust conditions out in the Kuiper belt, as well as the environment that Pluto lives in, as well as optical navigation so that we could do targeting burns, because we had very precise arrival time and spatial window constraints. In order to do the atmospheric occultations, we had to fly through a 100-kilometer by 60-kilometer box and arrive within 9 minutes of the scheduled time that was chosen at launch. So we did a lot of optical imaging of Pluto against star fields, shipped those data back to Earth over the Deep Space Network, and closed the solution to do burns to get the timing and to get the aim point correct. In addition, John Spencer, who will be the first speaker in the next session, ran a hazard analysis team that was looking for rings or satellites or other debris in the system in case we had to do a divert maneuver to one of those other flyby targets. Fortunately, we didn't have to do that. The majority of the data that you'll be seeing throughout this meeting were collected in a 9-day period right around closest approach in July of last year. But we also took high phase data after we left the system. We took a lot of approach data. I'll show a little bit of that, and you'll see a lot more in future talks. Let me say that the data transmit from New Horizons takes 16 months. And that green arrow shows you where we are. We're about halfway through the data transmit. So all the results that will be shown at Lunar and Planetary's science conference this year only involve the first half of the data, because the other half, no one's seen it yet. Now, that long transmit is primarily the result of that telecommunications decision that we made. If we'd have been at Voyager data rates, we would have gotten all the data to the ground in something like 6 weeks. But if we'd had Voyager data rates, we'd have never made the cost target. And then we would have been canceled as well, I'm quite sure. So again, if you're writing discovery proposals and New Frontiers proposals, that's a real lesson learned. We actually got it done because we made compromises. And then we conducted hundreds of scientific observations in the Pluto system, ranging from stereo and color and composition to atmospheric spectra, the plasma data, et cetera. To my knowledge, to everything that we've seen, every single observation worked. We don't have a single failed observation from the close approach. And that's pretty amazing for a single spacecraft mission that couldn't do a practice for the flyby. And I think it speaks to the hard work of our team writing all that software and all those command sequences and testing them over and over and over again. So now let me turn to the actual science. And in this talk and in other talks, you'll hear us use names of surface features on Pluto. As you all know, these are all informal names that our team uses. We have not submitted them to USGS or to the IAU. But there's plenty of good stuff, and we need to be able to refer to surface features. And so you'll hear some of those names beginning with my talk. I want to start by talking about the small satellites. For those of you that don't know, Pluto's satellite system has 5 objects in it. 4 of them are small, orbiting beyond the binary. And they are shown here from left to right in order of their Pluto-centric distance. So Styx is closest to the binary and Hydra is farthest out. All of these objects were discovered by the Hubble Space Telescope between 2005 and 2012, and they were never resolved prior to the flyby by New Horizons. You can see the scale bar there. They're of scale 50 kilometers across for the 2 larger ones and more like 10 kilometers across for the 2 smaller ones. They all turn out to have very high albedos, as high as Pluto, much higher than Charon. And they seem to come in 2 pairs, small and large, and then small and large. And that may be telling us something about the disk out of which those satellites formed, but I think it's too early days to really know for sure. We're finding mysteries in this satellite system, and you'll hear more about this from Simon Porter later. But one of the discoveries that we made from doing photometry on the satellites is that unlike the Pluto-Charon binary, they are in excited rotation states. They are not synchronously rotating. Even though the damping times for these objects are short compared to the age of the solar system, they are being rotationally excited. And in fact, Hydra, which you see looks like a football tumbling there, turns about 100 times on its axis for every time it travels around Pluto. It's truly an amazing system, a dynamicist's delight. Now I want to say a few things about the big satellite, about Charon, which, if you're not familiar with this object, it's like a mid-sized icy satellite. It's 1,200 kilometers across, and it's primarily a water ice surface. We knew a little about it prior to the flyby, but in the flyby we learned many other things, and you'll be hearing about that as well this afternoon. I just want to say you can tell just from looking at this beautiful mosaic of the system, of the satellite rather, that there's lots and lots to do with Charon. It is a fascinating object. We have determined that it has no atmosphere down to picobar levels, unlike Pluto. That's 1 million times lower than the pressure on Pluto for our upper limits. We've discovered that it's a very heavily cratered surface, that there are vast extensional tectonics, as you can see, that its pole has an oddly red-colored stain that you'll probably hear about from Will Grundy. We think may be related to atmospheric transfer from Pluto onto Charon and cold trapping at the pole. There are many mysteries on Charon, and I'm sure that many of you will want to work on this object. Kelsey Singer and others have been age dating the surface for us by counting craters, Stuart Robbins as well. And of course, we can only count the craters on the encounter hemisphere, which we can see at high resolution. But they've counted now hundreds and hundreds of craters and derived a surface age that's very old, 4 billion years old. In addition, they've been counting craters on the two larger of Pluto's small satellites, Nix and Hydra. And they also turn out to be about 4 billion years old. So for the first time now, we think we can age date the satellite system formation. We always had circumstantial evidence that the Pluto-Charon binary and its satellites were created in the distant past, but we never had data to support that. And now we can show it, thanks to New Horizons. Okay, let's turn to Pluto and talk about Pluto itself. Pluto is a slow rotator. It turns on its axis in 6.4 days. So on approach, we wanted to make imagery of the entirety of all of the visible terrains that were presented to us, and that's what we did. The close approach hemisphere is shown here near the bottom, near 6 o'clock, in color. This is the close approach hemisphere in all of its glory. It is a spectacular object. There's a little bit of something for everyone, whether you like atmospheres or glaciology, or you like tectonics, you like surface composition and color variations. Let me show you some examples. I'm going to start with this perspective view as if you were several hundred kilometers above Pluto's surface, looking down on the most prominent feature on the surface, which is the western half of the heart, which we informally call Tombau Regio. This western lobe we call Sputnik Planum. It is a 1,000-kilometer scale nitrogen ice feature. It is a cold trap to the volatiles on Pluto's surface. And it is such a prominent feature that we saw evidence of it even from Earth in Earth-based data, but we could see this feature from more than an astronomical unit away. It's spectacular. We believe that although the ices there are young, because we can't find any craters on the surface of Sputnik Planum at any resolution, down to 70 meters per pixel in high-resolution strips, that the actual structure itself is an ancient impact basin. And you'll notice that it's ringed by mountain ranges that tower 3 to 5 kilometers above the plain. But there's a lot more in Sputnik Planum than just an impact basin with ice. We see evidence of sublimation, thousands and thousands of sublimation pits with characteristic scales of 1 to several kilometers, and evidence for flows in the ice that you can see where those distortions in the patterns are. Up in the north, we see flow patterns that are different. And here I want to point out a number of things. First, just casual inspection, you don't see any craters. Secondly, you'll notice that where there are obstacles to the ice, which appears to be flowing towards the shoreline, for example, those islands that are protruding upward, we can actually see the flow lines and the dynamics of the ice. The ice is moving. If you look a little more closely, you'll see ovoids or polygonal patterns in the ice with horizontal scales of tens of kilometers. We believe that is due to convection in the ice, and that it's that convection that is erasing the craters that are forming on the surface and keeping the crater retention age low. You'll hear more about that later today. We also see evidence of flow into Sputnik from the highlands down these chutes where massive 50-kilometer scale flows have taken place in the recent past. Just an amazingly dynamic place. This image that was created by John Spencer very recently in the last week shows you some of the complex patterns and some of the headaches that Sputnik is already giving us. There's a lot going on here. And it's going to be a job for many of us in this room over the next many years, I think, to really understand this feature, which has no real analog anywhere else in the solar system. In the color and composition, we see gradients as well, and they don't seem to obviously correlate in some simple way. So we have a lot of work cut out for us in that as well, and Will Grundy will be talking about that in about an hour. We see evidence for what may be large cryovolcanoes on the surface of Pluto. These are clearly constructional features with scales of 100 or 150 kilometers and very large central pits or potentially caldera at their summits. You'll hear more about that as well. And for those of you that think that all of the terrains on Pluto are young, like Sputnik, that's not the case at all. There are ancient terrains on the surface as well, and you can see this. This is actually at the interface between Sputnik Planum and a broad expanse we call Cthulhu, the darker region. It's very heavily cratered. It's as old as the late heavy bombardment. Just like Charon and the small satellites, we've been age dating on Pluto as well, and I think the most interesting result is that we have found a wide variety of surface ages. Sputnik itself has only an upper limit crater retention age of about 10 million years. Cthulhu, more than 4 billion years old. But what is particularly interesting is that we find intermediate age terrains as well. And that tells us that Pluto has been active throughout its history, that Sputnik is not a recent anomaly on a dead world, that Pluto has been active throughout this entire period, and that's certainly something that I never expected, and I don't think very many people did, because it's such a small planet. If you're interested in atmospheres, you're probably at the wrong meeting at LPSC, but nonetheless, I want to say a little bit about Pluto's atmosphere, which we discovered, as I said, back in the 1980s. It was discovered with the Kuiper Airborne Observatory. Before New Horizons arrived, we had atmospheric occultations that were done from the Earth and from airplanes flying over the Earth. And there was a controversy about whether some of the vertical structure might have been caused by hazes or not. And we really never could tell. But here, New Horizons solved this problem in 15 minutes. It took this image showing almost 24 concentric haze layers. This is a forward scattering image made about 15 minutes after closest approach. And our atmospheric team has been thinking a lot about how these hazes get produced. They're very much reminiscent of the detached haze layers high in Titan's atmosphere. And of course, Titan also has a nitrogen methane atmosphere like Pluto's. But there's now a growing consensus on our team that the structure that you see, that horizontal banding or layering, is organized by gravity waves, not cosmological gravity waves, but atmospheric buoyancy waves created by the flow of the atmosphere over the steep topography of mountain ranges. And you can see that their models agree pretty well with the kind of phenomenology that we actually see. Another interesting result in terms of the atmospheric science, remember, one of our objectives was to measure the escape rate. It was thought that because Pluto is such a small planet, that its atmosphere would be very large, like a cometary coma, and that it would be escaping at rates of 10 to the 28th molecules per second, give or take. That turned out to be completely wrong. What our atmospheric occultation with the UV spectrometer, with ALICE, showed us is that, in fact, the upper atmosphere is about 40 degrees colder than Earth-based models had indicated. That means the atmosphere is more compact, the scale heights are smaller, and so the atmosphere is held more closely to the planet, deeper in the potential well. In addition, because it's colder, the individual molecules in the atmosphere have less energy. And those two things combine in an exponential term in the escape equation. And the end result is that our understanding of the escape of Pluto's atmosphere has completely changed from before the flyby to after. In fact, our best estimate of the escape rate today is a few 10 to the 25th, 500 or 1,000 times less than we thought before we went there. Really quite an amazing change. We have been hard at work, not just downloading data, going to DPS, going to AGU, and now LPSC to give dozens of talks at each meeting, but we've been writing papers as well. We're trying to be as productive as we can, as quickly as we can. Our first paper was published in Science in October, 94 days after the flyby. That was a lot of work for a team that had basically been working around the clock on Encounter for 6 months. We followed that up last week with 5 papers that were in Science, the March 18th issue, and the 5 papers correspond one-to-one to the 5 talks that follow this Masursky lecture. A paper on the geology and geophysics by Jeff Moore, a paper on the composition by Will Grundy and his team, a paper on the satellites by Hal Weaver, a paper on the atmospheres by Randy Gladstone and the atmospheres team, and Fran Bagenal and her team's particles and plasma paper. There's a lot in this. Each paper individually reports dozens of discoveries. You'll hear about many of them this afternoon. I want to say a word in recapping the mission, and then I'm going to talk about a couple of other aspects that I think are important. We really did it. I never get tired of saying we did it. That we actually did a breakthrough Outer Planets mission in terms of cost and schedule. And we met or exceeded every objective that we promised at the time that we wrote our proposal. And for those of you who are interested in working on these data sets, our first delivery of Pluto data sets to the PDS is only a few weeks away. It's next month. And NASA plans a call for DAP proposals this year. So you can get started thinking about what proposals you want to write, because there are many challenges in these data sets, as you will see. And in addition to the 6 papers published in Science and 1 that we have submitted to Nature, there's a special issue of Icarus, which we've also submitted quite a number of papers to. I think our total, which is changing day by day, is now about 20 papers submitted or published, and we are 8 months past the flyby, only halfway through the downlink, and very happy to be already getting results out. I want to now advertise the proposal that we're writing for an extended mission, because we built this mission to explore the Kuiper Belt. In fact, NASA's AO called this the Kuiper Belt Pluto mission to emphasize the context. And we were required, as the other teams were, to build the spacecraft to be capable of flying on for years, to have the communications range, the sensitivity in the instruments, the fuel on board, et cetera, to take advantage of having a spacecraft in the Kuiper Belt. And that's what we're proposing to senior review next month. The centerpiece of our extended mission proposal is a close flyby, much closer flyby than the flyby of Pluto, to a small Kuiper Belt object discovered by the Hubble Space Telescope for New Horizons. Actually, our team led that observing campaign. The object is called 2014 MU69. We don't know its size, but we can make good guesses about its albedo and therefore derive its size from its brightness. It's somewhere between 20 and 40 kilometers across. So it's like the scale of Eros. In that diagram that shows a little cartoon depiction of this object against the state of Massachusetts, if you look carefully, you'll see Rosetta's comet, Comet CG, next to it. This is an object that's probably 1,000 times as massive as that comet, or a typical comet that we've done flybys of. So it's going to be very interesting from the standpoint of understanding planetary origins to fly by an object in this intermediate size class between small planets like Pluto and comets like 67P. This object is known from its orbit to have an extremely high probability, 96 or 97%, of being a cold classical KBO, meaning its origin was not somewhere dramatically closer to the sun, but actually out in the Kuiper Belt. This is the one portion of the Kuiper Belt population that we know was formed in the Kuiper Belt. So it is an anchor point to understanding the composition of things in the nebula at very large distances like this. And it's an object that's always been cold. Unlike all the comets and all the other small bodies that we've flown by, this is probably our opportunity for the most pristine object anyone has ever been able to study. And the flyby, which we've already targeted with NASA's permission, will take place on January 1st, 2019. But that flyby is only the centerpiece of a much more comprehensive investigation of the Kuiper Belt, which I want to tell you about. We have 4 other objectives for the extended mission, which will stretch from 2016 to 2021. In addition to making a close flyby of MU69, we're also going to be close enough in range to study quite a number of other small KBOs and some large ones that are Pluto scale, and to study them in ways that you could not from the Earth. Because we're closer, we have better resolution, and we're able to look, for example, for satellites at close-in ranges that you just can't probe from the Earth with any technique, even with the Hubble. In addition, because we'll be observing these objects as a function of their solar phase angle, we'll be able to take advantage of our changing geometry to recover their Hapke parameters and to actually have a statistical sample that we can place MU69 in context. We'll be making other studies as well. I think one of the most innovative is that because we're looking back on the rest of the solar system, the Kuiper Belt, the Centaur population, for example, we're going to be able to study another 18 or 20 small bodies to determine whether or not the recently discovered rings around the Centaur Chiriclo are a common occurrence or something anomalous. And I don't know of any other way in the next several years, except through New Horizons, that we can develop a data set like that. Our plasma instruments and the dust instrument are going to be busy the entire time, essentially continuously taking data. And I know that most of us are not plasma scientists, and the study of the heliosphere is not the top of our list. But if you're interested in the space weathering of KBOs or Pluto or its satellites, you should be very interested in our understanding the plasma environment, which is weathering those objects. And you should be very interested in the dust environment, which is also affecting their surface regoliths. I know I am. We've also been asked by NASA to potentially repurpose New Horizons late in that extended mission, if it's approved, to do some kinds of astrophysics that the Astrophysics Division would like to have a ROSES call for. Some of you will remember that Voyager was used the same way in the 1990s. And so I'm very happy if New Horizons is able to contribute to something more than even planetary science. And so we're making that option available to NASA as well. As I said, we flew 9.5 years and 3 billion miles to get to our target, the Kuiper belt. Not just Pluto, but the Kuiper belt. And this is a complicated diagram, but the dots on there in the upper left in particular just show the distant Kuiper belt flybys of different targets as a function of date. You can see that New Horizons will be busy each and every year making multiple KBO observations so that we really develop this fantastic data set by the end of the process that gives us one KBO up close with as good as 25 meter per pixel resolution, 3 times better than anything obtained in the Pluto system. In addition, studies of dozens of other KBOs. Well, now I'm going to turn to just about the last thing I have to say, and Steve asked me to talk about this. For all of us that got to work on New Horizons, the flyby was an unbelievable experience of scientific discovery. And I think for most people on the team, you won't hear these words said very often at a Masursky lecture, much less at any LPSC talk. It was emotional. We worked very hard for 15 years to build that spacecraft and get it launched and get it across the solar system. And Pluto turned out to be spectacular, and so did its satellite system. This is actually the science team at the moment that this image was first revealed, the morning of the flyby. And look at the emotion that's going on in that room, the scientific emotion. But it wasn't just our science team that was interested. The public turned out in droves. And I think this is a very important lesson for our entire community. People really love exploration. They love what we do in planetary science. And we worked very hard before the flyby, for years, to try and drive public interest in Pluto, to try and drive interest in New Horizons, to show what exploration is all about. This is a scene at APL, the Applied Physics Lab, in their largest auditorium on the morning of the flyby at the time that the spacecraft was making closest approach. And I want to give you a couple of other metrics. We got the Google Doodle. Can't beat that. New Horizons was on the cover of 450 plus newspapers above the fold on the same day. Countless magazines, from National Geographic to astronomy magazines, and the response on our website was literally unparalleled. They had 10 times as many visitors on flyby day as MSL had on landing day. People love exploration. And I want to tell a couple of stories because I've got a couple of minutes left, and I promised a couple of people that I would do this. Those metrics, 458 newspapers above the fold on one day, 1 billion visitors to your website, magazine after magazine. Those are great metrics. But I've been giving public talks on New Horizons, and so has our team, every single week since the flyby. I don't think I've missed 2 weeks, and I think I'm pretty typical on our team. We get asked to give a lot of talks. We give a lot of talks. And after the talks, people line up, sometimes for over an hour, to ask questions or to have their picture taken with you or with a picture of Pluto or something. It's really a very emotional response from the public. And I want to tell 3 very brief stories. Last August, I gave a talk at a convention of telescope makers. It's kind of a maker fair for those people who build telescopes themselves. This is up in Vermont. And it was a talk at 9 o'clock at night, and after questions ended, it was 10:45, and a line formed for an hour until almost midnight. In the middle of that line, a young woman in college got to the front of the line, and she said, "People say that our generation doesn't have the same chance that our parents' generation did to do great things. And she said, thank you, New Horizons is the best thing that's ever happened in my lifetime. I was getting off a flight on a trip from Tucson back home. I was wearing this very shirt, New Horizons shirt. And as we were getting off the flight, the pilot, as they sometimes do, was greeting everybody and thanking them for flying on their airline. And he said, hey, that's a New Horizons shirt. I said, yeah. And he said, you work on that? I said, I do. He said, I just got to tell you, that's the coolest set of names, science fiction names, and what you're putting on Pluto and Sharon. He said, but I got to tell you, my wife and my 3 kids and I, all 5 of us, have New Horizons screensavers. That's pretty amazing. And then just about a week ago, I was in Florida, and I gave a talk to a convention of business executives. And again, a long line formed, and in the middle, this actually happened. A woman came, and she was crying. And she said, my son was a DNF student until he watched the New Horizons flyby. And he decided he wants to be an engineer. And now he's an A student. And you saved his career. Things like that don't happen to us as scientists. But New Horizons has shown that we can really reach people beyond ourselves and the great science that we all do, and the things that we put in textbooks that change our understanding of the solar system. That we, as a community, can reach out and inspire the world. The things that we do at NASA change people's lives. Let me end with this great flyover of Pluto. Images made by the LORRI camera on board New Horizons at a resolution scale of 70 meters per pixel. This is Sputnik Planum, up on the shore of the Aladrisi Mountains and out into the highlands beyond, towards the North Pole of Pluto. The data sets that you're going to see in the next 5 talks are mouthwatering, and it's going to take years to understand it all. We can't wait, and I hope you'll come and join us and write some of those proposals. Thank you very much for New Horizons team. Thank you, Eileen. Okay, thank you very much. Well, I said it'd be a little bit different. But also, for Q&A, I think we've got 5 or 6 minutes, so you're going to moderate?
Yeah, since we do have to turn the room over, we need to keep the Q&A short, but we do have time for 1 or 2 short questions. Otherwise, okay, you.
So just very quick, you just showed that beautiful flyover, but can you give an impression of scale or apparent altitude of those images we just saw? How high above Pluto were we, or how large was that area?
Yeah, so those images were 1,000 pixels across at 70 meters per pixel, so you can do the math. They were like 70 kilometers across, and it's as if you were flying over in a high-altitude airplane.
Chris Peterson, University of Hawaii. How much is known about the eccentricity of the orbits of Pluto and Charon around their barycenter, and is it possible that they're eccentric enough for the libration to be pumping some heat into the interior of those planets?
Well, Pluto and Charon are completely tidally evolved. They are spin, orbit, locked. And to the best of our knowledge, there's no tidal energy being exchanged between the two. The binary is probably exchanging tidal energy with the small satellites that orbit out beyond. And the eccentricity of Charon's orbit is 0, according to Mark Bowie.
Okay, thank you everyone, and we're going to quickly reset for this afternoon's sessions, and I'd like to thank Dr. Stern again.
Thank you.